Well, hello everyone, and welcome to this sixth of 8 presentations by renowned climate scientist, Dr. Tom English, in his environmental education series. And this one's on nuclear and what does it mean for us. My name is Dave Rice, and I'll be your host for this event. Dr. English has accomplished many things in his rich and varied career, much of it having to do with improving our environment, and we all owe him a ton of debt. He was the author of the California Clean Air Act in the late 80s, which was largely responsible for getting rid of all of the smog we suffered from back then. Y'all remember that? He's met and collaborated with dignitaries around the world and has earned a Congressional Medal of Honor on behalf of the Patriarch Bartholomew for their work on climate. And one of the things I appreciate the most about Dr. English is that he has an unusual ability to communicate difficult concepts in very easy to understand ways. He has a huge passion for educating others on our current climate crisis and the existential threats that it's bringing to us and to our children's generations. And we all need to be aware of what can be done to counter this. So the goal of this series is to help you more clearly understand the main issues behind climate change and what can be done about it so that you can have a better discussion with family and friends and become more involved in helping make a difference. So without further ado, it's my pleasure to introduce Dr. Tom English. Welcome, Tom.
Thanks very much, Dave. I sure appreciate it. I'd like to welcome you all again. This is going to be a fun-filled afternoon, so let's get on with it. And this is a special day, the day after St. Patrick's Day, celebrated by all. I've always thought of myself as very sympathetic to the Irish. Whenever I was at the appropriate age, I took my confirmation name as Patrick. So it's been a big thing for me. And I'd like to basically tell you a little story about that. The story involves the Patriarch Bartholomew, who you can see, he's the guy with the long beard in the middle there under the painting. And this is an activity that's taking place on an island somewhere in the Sea of Marmara near Constantinople. And several of my friends and I were involved in making a presentation to the Patriarch Bartholomew of the award for the steward of God's creation. And this is my part of the presentation. So I get started. I'm kind of nervous. I'm not used to getting up in front of a guy that's been, that runs a church for 300 million people. So it's something I don't do every day. So I'm kind of nervous, and I basically start saying the hello part. And he interrupts me before I finish my first sentence. And he says, "English is a very strange name." So what do you do when that happens to you? Do you basically ignore it so you can get on with the rest of your speech, or do you play it? So I decided to play it. So I explained to him how my ancestors came from England to Ireland in the year 1000 and how they became eminent there and had a good time there. And I did it in such a way that everyone was laughing. That's why everyone's laughing in the picture there. So I just wanted to share that little story with you. So this is a picture of a book that's written by a friend of mine, Dr. Greg Giasco. Greg was chairman of the Nuclear Regulatory Commission for about 4 years or so. And he was also in addition to that, he was also a member of the commission for several years. So he really knows this stuff very well. And his book title is really precious. It's called Confessions of a Rogue Nuclear Regulator. So if you want to learn a little bit about how things worked in the NRC, especially around the time of Fukushima, this is a really good book to read. This is a picture of me giving a presentation at San Onofre that appeared on the local public channel. The basic idea is up here is a link for you if you're interested in hearing. I think there's 3 presentations on that link, me and several of my friends. That's how you can get to it. If you have any questions about the link, Dave can help you get to that. So today we're going to continue on this effort to look at the complete energy cycle. Before we did it for 4 different kinds of electrical power systems. We did it for coal and natural gas and wind and solar. So today we're going to apply the same thing to nuclear. And I'd like to just remind you that this methodology can be used to examine almost any system. So it's a really general kind of methodology. We'll start with building the plant, go through the fuel cycle. That means getting the fuel to run it, the uranium to run it, and running it in a power plant, taking care of all the issues that go on there. And then finally, whenever you're done, decommissioning the plant and getting rid of it. So those are the 3 steps. Before, we went through a description of the natural gas, coal, solar, and wind. And we basically found out that things like mining and transport and processing were very, very important in terms of the impact of those energy systems, but not so important in terms of wind and solar. So basically, the analysis of a wind and solar plant is much easier than natural gas or coal plants. Now, if we extend this to nuclear, we find out that everything is important in examining a nuclear power plant. So we basically get to a very complicated kind of interaction. And I'll try to guide you through that. So let's first of all build the power plant. There are a couple of curves here that are interesting. This is from an article about why America abandoned nuclear power and what we can learn from South Korea. But there are a couple of curves here I'd like you to look at. One is this curve, which shows the cost, bucks, dollars, vertical, and the date that the construction started. And what you see here is what you'd expect for any kind of new technology. The price drops. But in the case of nuclear in the US, it stops dropping and it starts going up, up, up. This is the contrast with, say, France, where during the same period of time, you see the drop, but you don't see the going up there. This is due to various things. We tend to like, in the United States, large nuclear power plants. This is a comparison of the US data, these dots, with the world average. And you can see we're considerably above a construction time to build plants. And you know, time is money. So if you spend more time building it, it just costs more. So that gives us some idea of some of the problems. Some of those are going to be social problems, like maybe our people are a little bit more picky than the French were. That has to do with things like how much subsidy does the French government give compared to the US government. But somehow or other, our costs got out of whack. One of the reasons they got out of whack is because we decided to make every nuclear power plant different than the one before it. So we have no 2 power plants that are the same. Whereas the French used the cookie cutter approach to their nuclear power plants. They tried to make it as much the same as they could. So if you make things the same over a period of time, you learn how to do it and it gets cheaper and cheaper. If you make each one unique, you don't have that learning curve. So let's look at the fuel cycle. This is the ordinary fuel cycle for uranium. Basically, the uranium ore is mined at a hole in the ground or a surface mine. There's a lot of issues involving the health effects of the workers there. Many lawsuits still haven't been settled. The uranium is then processed into a material that's called yellow cake. And then the yellow cake has gone into some chemistry functions to turn it into a gas, uranium oxide, and then to another gas, uranium hexafluoride. This gas is then enriched. What that means is that the way we design our nuclear power plants is they won't work with ordinary uranium. That's enriched to, it has U-235, about 0.7% of it is U-235. The rest is U-238, and that's not useful for these kind of plants. Anyway, they take this gas and they enrich it from about 0.7% to about 4% or so. And that's enough to basically cause our nuclear power plants to work. So it's converted into little pellets, and we'll show you some examples of those in a minute. Those pellets are stuck into assemblies and they're put into the power plant, and things are run for a while. And this basically talks about taking care of the waste, and we'll spend a lot of time on that. This is a typical site in the West where you would get uranium. These are some so-called uranium tailings. This is the stuff that's left over after you get the uranium there. And we've been fairly casual about that. We leave it near the river streams and so forth. and there are problems about water supplies, like the water supply to Los Angeles, for example. That was an issue. So the nuclear industry and the government constantly finds itself in court fighting over the way they treat these things. The materials then converted into those gases we talked about, and this is a Paducah, Kentucky gaseous diffusion plant. It's a big plant. It takes about 3,500 acres. It takes a lot of water, 26 million gallons per day. It has 9 miles of railroad associated with the plant. So this is a big plant. And this thing uses electrical power at about 3,000 megawatts. So that would be roughly 1.5 times the power that used to come out of San Onofre. So this is a big, expensive, power hoggish kind of plant. And that was used to basically take the uranium from 0.7% and get it up to around 4%. Now today we have kind of a different way of powering the nuclear power plants. Not all of them, but a lot of them. We basically are powering the plants with used nuclear warheads. How about that for an idea? Used nuclear warheads. Both countries, Russia and the United States, used to have about 50,000 warheads pointed at each other. This was during the days of MAD, mutual assured destruction. The idea that you wouldn't do anything because the other guy was crazy enough to wipe your society out, but if you got yours wiped out, his would be wiped out automatically. So it's a sort of a suicide pact. So anyway, we've decided to reduce those numbers down to a few thousand or so. That's through the Strategic Arms Reduction Treaty. And that's still way too many nuclear warheads, but it's a lot better than 50,000. So we made some progress on that. I was involved in a activity at the Rose Bowl where we were trying to get the government interested in doing something about this. And we gathered 105,000 people into the Rose Bowl in favor of the so-called nuclear freeze. So it really worked. Now what they do with this fuel is both sides, the Russians and the US, contribute their warheads. They go into a plant that takes the uranium or the plutonium out of there and basically puts it into a form where it can be mixed with ordinary uranium into a fuel that's called MOX, M-O-X, metal oxide fuel. And then that fuel goes through the normal process of being made into these little pellets and so forth and so on. So we have really two different fuel cycles here, one involving warheads, kind of a strange condition. So we take these little pellets that you can see are smaller than your thumbnail, and then we stick them into a cylinder, a long, skinny cylinder, looks like a long spear, maybe 15 feet long or so. We call that thing a fuel rod. So what you do is you put some little springs at the end of it to keep the little pellets in firm contact with one another. And that gives you one unit of what shall we call it, of the system, the fuel rod. We then take these fuel rods and we put them into a checkerboard-like structure. And we have maybe 15 holes on one side, 15 holes on another. So in one of these structures, we can put 225 of these fuel rods. So that constitutes a new thing called a fuel assembly. Now we take that fuel assembly, and that's the basic thing that goes into the nuclear reactor to give us the heat that we want to from the reactor. When we're done with the fuel rods, what happens is these are only good for so many years. It's kind of like if you recall the old light bulbs, they used to get a coating of dark stuff on them, and they got dimmer and dimmer over time. And so they weren't functioning as well. Well, these fuel rods are like that. The waste that collects inside of these basically causes the whole system to become more and more inefficient. And so when it gets to a certain level of efficiency after several years, what you do is you take this back out, you put it into a jacket like this, and you put that into a spent fuel pool. It's like a swimming pool. And the reason you put it in a swimming pool is basically to keep the radiation from harming people. The top of that fuel assembly would be under about 20 feet of water. Now, in terms of nuclear waste, there are actually two kinds of nuclear waste. There's fission nuclear waste, which is basically, these would be smaller particles that are intensely radioactive and basically die off fairly quickly on a big time scale. And then there's fusion particles. We don't talk about those too much. These are the ones that are deadly poisons like plutonium, and they last a long, long time, the order of 25,000 years would be the half-life of a typical plutonium. So let's go through the fission process first. What we have is some of this enriched U-235, and we have a neutron floating around there at the right speed. The neutron hits the U-235, and the U-235 gets all excited and splits. In this case, it's splitting into a cesium atom and to a rubidium atom. So that constitutes some nuclear waste. Now those may in turn split down into other things or stay the same. So there we have nuclear waste of the fission variety. Now what happens in addition to just splitting the atom, when you split the atom, you get a lot of energy. So you're getting the order of 200 million electron volts of energy out of there. Plus, in addition to the energy, you get two neutrons coming out. So remember, you started this whole thing with one neutron going in. Now you get two neutrons going out. So for every one that goes in and gets captured, you get two out. So you're starting to get into what's called a chain reaction. So these two pieces here can, again, each split and give us 4 neutrons. They can split again, give us 8, and so forth and so on. So what happens is you have a chain reaction which can be dangerous if you don't design it right. This is how a nuclear weapon works. You basically design it so that chain reaction just continues and you don't waste these neutrons. Whereas in a commercial power plant, what you do is you allow this to go on a little bit, but what you do is you control it using some so-called control rods, and that keeps everything safe. So this is how the fusion process works, and people normally don't talk about that too much. This is a atom of the uranium that's not too useful, the U-238. It doesn't do anything in terms of the normal heat. So that atom gets hit by a neutron, a different speed neutron, and it gets captured and it becomes a new form of material. It's like the old sorcerer's trick of turning lead into gold. So what you're doing here is you're converting uranium into a different form of uranium. This form of uranium has one more neutron than the other. So basically, instead of 238, it's 239. And this turns out to be unstable. So in about 23 minutes, this thing gives off an electron and becomes a new element called neptunium, 239. And now since it gave off an electron, it has 93 protons in there. So basically, we upped the scale. And we take this neptunium and allow it to sit around for a couple of days, and it becomes plutonium. So now we have this very dangerous plutonium that can hang around for the order of 25,000 years is the half-life. So it means half of it's gone in 25,000 years. So when we design our nuclear waste repository to contain this stuff, we have to make sure that the stuff will be contained for that period of time or longer. This is how the reactor works. We take those fuel rods that we had before, and we basically stick these control rods in between them in order to keep the neutrons from exploding, essentially. And so what happens is this gets hotter and hotter. Water is pumped in, water is pumped out. The hot water then goes into another container here, a so-called steam generator. The heat comes off of there, generates steam. The steam comes out of a pipe, goes into a turbine here, something that the steam will spin around, and this causes the electrical generator to spin around, and that causes electricity to come out. So that's why we do the thing. Then we take the water that went through the steam turbine and go through a condenser. We want to save the water because water is expensive, and basically we repump the water back in. So that's how the system works. This is an example of a nuclear reactor that went wrong. This is a so-called Mayak explosion. I would assume that very few of you ever heard of this one. It occurred in Russia, in a town that was since taken off the map, at Kyiv, Russia, in 1957. I first heard about it in around 1977 at a meeting at the old executive office building in Washington. And we heard about this thing, but it was real hush hush, so it didn't appear in US newspapers until around 1993 or so. So what happened there is this whole thing blew up. It was a combined power generating plant, but also a reprocessing plant. It blew up. And what they did is they basically evacuated everybody. And they put the town off limits for all the order of 40, 50 years. It's still off limits today. So this is an example of a disaster gone bad. And there were many deaths associated with it, the order of 10,000 or so deaths. This is 3 Mile Island. This is near Philadelphia, essentially. And this happened in 1979, where basically one of the reactors melted down. They weren't quite sure what happened. There wasn't any external smoke or anything you could see from the outside, so people were kind of confused as to what went on. But it was a meltdown. And this happened about 10 days after the movie The China Syndrome came out. So the tickets to the China Syndrome soared as a result of this 3 Mile Island. So this basically showed that this could happen in the US. This is Chernobyl. You're probably all familiar with that. This happened in the Ukraine, basically putting out an awful lot of radiation all over Europe and a good bit of Russia. The KGB had decided that when this thing blew up, that they would not issue any iodine tablets. Iodine is usually issued if there's an explosion like this, because the radioactive iodine gets collected by your thyroid and will cause thyroid cancer. So what you would normally do is you would issue these tablets. People would saturate their thyroids with iodine, and so the iodine would just pass through the rest of your system and you wouldn't get cancer of the thyroid. So what happened with these guys, they decided they were more nervous about people getting upset about the explosion than about getting cancer, so they didn't tell them about it. So this all hell broke loose over that. This is the Fukushima plant. 6 reactors here. Nice looking plant. And reasonably well designed. They made some mistakes in terms of the elevation of the plant from the water, and their electrical system basically could be taken out by a tsunami. So what happened is the thing, first one of these reactors blew up, another one blew up, and the third one blew up. All 3 of them melted down. And it looked like this. Big, ugly looking scars upon the earth there. It's still a mess today, and they're not quite sure what to do with it. One of the commonalities of all of these accidents that I noticed is that they all involved zirconium alloy, that's the coating on these fuel rods, and water. It turns out if you get a high temperature, high enough temperature here, the zirconium will react with the water to produce an oxide of zirconium and hydrogen gas. The hydrogen gas, you're all familiar with the Hindenburg explosion, can explode. So the explosions of all 4 of those plants, we believe, is due to this reaction here. There's the Hindenburg there. So it's a scary kind of thing. And the thought when Fukushima happened is that it's very, very unlikely for one nuclear power plant to ever explode. But you would certainly never have 2 exploding. That could never happen. And certainly you could never have 3. So what happened is they had 3 explosions there. This caused all kind of havoc with the rest of the system. They weren't able to pump sufficient water into their spent fuel pool. And so the water that kept the spent fuel from overheating was getting lower and lower and lower. So the Prime Minister of Japan, Naoto Kan, was basically about a half an hour away from issuing an executive order to evacuate metropolitan Tokyo. That would be about 50 million people. And Naoto Kan is quoted as saying that we almost lost Japan. So that would have been devastating for their whole system. So anyway, this is the nuclear waste here. The waste products involve about 33 tons of uranium-235. So there's a lot of it in there that's still there, but you can't get it because of all the waste products. And there's about almost 600 pounds of plutonium in one San Onofre kind of reactor. So there are 2 reactors in San Onofre. So this tells you you're getting over 1,000 pounds of plutonium per year out of just like a place like San Onofre. That's one heck of a lot of plutonium. To make a nuclear warhead takes something like around 10 pounds of plutonium. So let's talk about decommissioning. One of the ideas is you take this waste and you put it somewhere safe so that it's not going to go anywhere for, who knows, 100,000 years or so, 25,000 years. And so they picked Yucca Mountain. It was chosen because of several things. It's away from people, far away from Las Vegas, at least. There were very few people in Las Vegas when they made the decision, not nearly as many as now. So it's away from people. It was on a military base, so it should be safe from any kind of terrorist threat. And the ground, the so-called tough geological formation there seemed to be adequate. There's a guy, Bill Alley, who ran the U.S. Geological Services function there to examine this geological formation for about 15 years. So he knows an awful lot about it. We've had many discussions on this. They've invested about $15 billion into that. It's currently not being used because of various reasons. And they estimate that in order to get the plant fully running, its life cycle cost of running the plant is estimated to be about $90 billion. So it's not cheap. This is a report of the world's nuclear waste in 2019 to give you some idea of where other people are, where other countries are. The French are planning to have a repository, and the repository is planned to open in 2035. I've been studying these schedules since the late 70s, and the schedules are usually about 10 years in the future, sometimes 15 years in the future, and that keeps floating. So this is now scheduled for 35, which is about, what is that? I would say 14 years in the future. This is the plan for Swedes. I was asked to go to Sweden by the Swedish government and bring my team from Caltech, JPL, and the Scripps Institution of Oceanography to study their plans. And we basically concluded that they did not have a scientifically defensible plan, that their calculations that they did were off by a factor of 10,000 in the wrong direction. So it was 10,000 times more dangerous than they thought. So anyway, their current plan is, again, roughly 15 years in the future. And Germany hopes to open one somewhere around 2031. So who knows what these numbers mean? I always think if just take whatever date it is and add 15 and get a rough estimate of the current plan. They really are having problems with this because it's how do you solve a problem where something has to last for a long period of time? Maybe we can talk about that during the Q&A. So basically that gets us started here. Let's talk about plutonium for a second. Ralph Nader came around and he made an estimate that if you had about if you had a pound of plutonium, that'd be enough to kill about 8 billion people. So what happens is if you have like a lump of plutonium, you could actually just put your hands over that stuff and keep your hands warm. Some people like Richard Feynman used to do that. But if you get a small speck of that into your lungs, it can be enough to kill you. So his estimate was a pound of plutonium. Others say it takes more than a pound. This one guy says it takes, a pound can only kill 2 million people. as opposed to 8 billion. So it turns out that another estimate comes out that says that the dose is more like 200 micrograms would be necessary. So it turns out that if you look at the amount of stuff coming out of, say, just those plants at San Onofre, we're talking the order of thousands of pounds, okay, thousands of tons. So that's enough to wipe out all of humanity. This is what the curves look like for the decay of this stuff. This looks like a witch's brew here. The radioactive particles, different ones, decay at different rates. This complex set of curves, each curve shows the behavior of one particular kind of atom. I think I have one for, this is for plutonium here. The plutonium, you see, doesn't do much here for the scale of maybe 10,000 years. It goes up a little bit, and then it hangs around for the scale of roughly 100,000 years. So if you have some plutonium lurking around, you're going to have it for a long period of time. One answer to the current problem is we have our waste stored at various nuclear power plants. That's basically because they don't know what to do with it. So if something ever goes wrong there, like if there is a terrorist attack or if there is a big explosion, then you're basically holding the people around that plant as hostages. So it isn't fair to do that. You should move the plant to some interim place so it doesn't threaten people. So move it out to the desert somewhere where it's a very low population in a place that's geologically stable. And if the geologists can't figure out how to do it for, let's say, 100,000 years, maybe you should settle for 10,000 years. You know, do as good as you can, because what you're doing is you're basically, if you don't do that, you're threatening the lives of those people that are near the plants. There have been various suggestions about what to do with the nuclear waste. Some people say take it out in the desert. Some locals here say put it in Southern California Edison headquarters. Some of them don't like how the Public Utility Commission has been behaving, and they say put it in the PUC headquarters. So we need to do something with it. So the solution that seems to be the favorable one now is to get the spent fuel out of the spent fuel pools and move it into dry storage. This is because of the problem at Fukushima that Naoto Kan said we almost lost Japan. So the idea is get it out of there and stick it in some dry storage place somewhere. The issue that I think we're having a problem with is basically we aren't being too careful about where we're sticking it. You know, we need to basically be more careful about how it's stored and where it's stored. Any questions, Dave?
One question has to do with Yucca Mountain, and apparently it sounds like there have been reports that up to $15 billion was spent building that over a long period of time, and whatever happened to Yucca Mountain? Why did it get shut down?
Well, lots of reasons for that. That's a great question. One is the behavior of the federal government. The feds tend to be pretty pushy on nuclear issues. And so they don't like to get much pushback from the locals. So they basically picked Nevada because it had the weakest congressional delegation. And they thought the geology would be okay. But basically there was a lot of annoyance going on there. So as soon as Harry Reid lost his position in the Senate, what happened is they immediately basically called the thing dead. You know, so what happens is if the government doesn't work well with the locals, with the cities, with the states, what happens is the people get angry about it. So one of the reasons is anger. My take on Yucca Mountain is that the geologist will give you a guarantee there for about 10,000 years. Now, right now, you just have the stuff sitting somewhere with no guarantee at all, right next to a big population center. So I think your choices are in favor of going with Yucca Mountain.
Okay, great. And then Mark is asking, doesn't the used fuel rods, don't they need to be stored in water?
The idea of storing them in water is two things. One is you get rid of the heat so that the thing doesn't heat up and melt itself. The other is that you keep the radiation away from people. So what they do is they put it in a big swimming pool, and basically they have about 20 foot of water over the top of the fuel rods. So those are the two ideas. Now you can take those fuel rods and stick them into an appropriate container, and you can solve the heating problem without any water. That's possible to do if you have the right design. So that's a good idea if it's designed properly. San Onofre, we'll talk about the details there, but what they did is they basically have some problems with their heating design, and they also have some problems with water, and we'll go into some more detail on that.
And then Robert asked probably the $64 million question that's on everybody's mind, which is that could some of this dry storage go critical?
The answer is what we did is we put together a group of people that looked at the situation at San Onofre, and it almost went critical. And I'll tell you about that as we get to the slides. But yeah, our position was we were damn lucky and really fortunate that we didn't have a meltdown there.
One more before we keep going. Larry's asking, is plutonium dangerous chemically or only as a source of radiation?
It's dangerous, I would call it biologically. What happens is if you breathe in some plutonium, it gets stuck in the alveoli of your lungs. And so it's essentially captured there. It's sort of like coal dust being captured there. And what happens is every once in a while, those things will spit out an alpha particle. So if an alpha particle hits your lungs from one of those captured pieces of plutonium, that can cause lung cancer. So that's the big threat, it's lung cancer. It can also get stuck in other parts of the body, like the thyroid and so forth. But one of the major biological endpoints is lung cancer. So let's talk about some of the San Onofre issues. This is it's the power plant I know the most about. I spent about 2 years working on the problem, so that's what I'm going to be talking to you about. Other power plants will have similar issues. So what the San Onofre solution was to basically take the spent fuel assemblies out of the spent fuel pool, stick them into a big basket. The basket would carry maybe 37 fuel assemblies, and then take that basket and stick it into some repository. Now what they did is they picked a repository that was 100 feet from the ocean. And this is how I got involved in this stuff. I saw this picture in the newspaper, and I thought, they wouldn't do that. No one would do that. This has got to be a mistake. Anybody that knows anything about high-level nuclear waste knows you don't want to store it, indefinitely near water. So you gotta. This can't be happening here. So sure enough, I was wrong, and it was happening. So this is what it looks like here. So we'll go through some detail of how this thing is constructed, but it's basically 100 feet from the water. And you might guess that there's a little bit of ocean water that gets in the bottom of those things. This is what the thing looks like when it starts out. These are cylinders, metal cylinders. These are guys. You get some idea of the size here. They're pretty big. We're talking maybe, what's that, 20 some feet, something like that. And what they have is an array of them because you can only stick one of those baskets in each one. And they're trying to get rid of all the spent fuel pool, all the spent fuel that's in the spent fuel pool. And it's interesting that they don't call it a high-level nuclear waste facility. They call it a ISFC. What an unpronounceable, weird name. ISFSI, Independent Spent Fuel Storage Installation. So if that won't turn anybody off, I don't know what would. So this is what it looks like. What they do then is after you get all this put together is you put dirt inside here. You put some concrete caps over the whole thing, and that basically is your assembly. This is what it looks like when you're done. So there's the two nuclear reactors, so-called, they brilliantly labeled them Unit 2 and Unit 3 because there was a Unit 1 earlier that they had already gotten rid of. So one of these things here will take one of those canisters that we talked about. So this is what it looks like. And you can see off to the right here, if you look closely, this body of water here called the Pacific Ocean. So it's really close. And some days, you know, when the waves are splashing out there, well, people were surfing out here. You see people on surfboards right out in front of us. So some days when it's splashing, you see water hitting the area there. This is the spent fuel pool again. Now we have our fuel assembly inside this jacket so that it can go inside these grids in the spent fuel. So it gets in a given location there. And you can see they keep it, the top of the spent fuel is about 20 feet underwater. These spent fuel pools are incredibly clean, and the walls are all stainless steel, so they're very expensive. This is the casket that we're talking about that would go into the ground for this isphacy. Basically, it's a circular casket, and these are the slots for the 37 fuel assemblies. So one of these goes into here, and then you get a second one. You do that 37 times until the thing is full, and it weighs, you're talking roughly about 54 tons. So it's a very heavy, very expensive thing. This is what the casket looks like when it's going into the hole in the ground. So these guys here are basically helping to put this thing in the ground. And you can see this tank-like machine here with these big tank treads is not a very precise kind of machinery. So the thing makes noise and shakes this thing around, it bounces. The tolerances are maybe 1/4 of an inch as it goes into this hole. So what happens is it gets banged from side to side, gets scratched on the way down. So this is not very good technology. One of my friends referred to it as Egyptian technology, meaning Egypt during the time of the pharaohs. This is an interesting guy here. His name is David Fritsch. He's referred to as the whistleblower. He, like many other people, went to this meeting of the Southern California Edison Community Engagement Panel. They had these meetings maybe once every month, every couple of months. And he was at the meeting just after they had an accident at San Onofre. And he was part of the accident team. So he listened to what they had to say in the meeting. Meeting went on for a couple hours, and they never said anything about the accident. What accident? There's no problem here. So he basically got up, and his speech went something like this. He says, there was a serious accident. It's involving the facility. I'm going to tell you about it because my kids have asked me to do that. I don't know whether I'm going to have a job tomorrow. So when he went on to describe what happened, and I'll give you the description that he gave me. He came to several of my talks. He used to enjoy coming to them because he basically knew how to do all the things, but he didn't know exactly the details of why he was doing them. So he's the whistleblower. By the way, he is no longer working here, and he's moved back to his home territory in Hanford, Washington, and he's selling real estate. So if you need any real estate in Hanford, David's a good guy to call. So this is how these things get started. We have the canister being pushed in this hole in the ground, and there's a shield around it, okay? There's a shield, and the shield is to keep the people from essentially getting exposed to intense levels of radiation. So the shield protects the people, and the canister is lined up with this hole in the ground. And so what you do is you put it in there, and you have cables holding it there to keep it from falling. And then it goes down lower and lower, cables let it go lower and lower, and finally it gets to the bottom. So that's what's supposed to happen. That's the basic idea. So what happened on the day that this whistleblower is talking about is there was a so-called near miss incident. It got down a little bit into the hole and got stuck. Now, they didn't know that it was stuck because it turns out the way this thing is designed, they cannot see what they're doing. They couldn't see what the cables were doing. They thought the cables were fine. So what they did is they decided that this thing was down the bottom here. And they basically took the cables and they basically had them laying around there. They were no longer holding this thing up. The cables are there to keep it from falling, essentially. So there was nothing holding it up there. It was just caught on the lip of a piece of metal here for about 20 to 40 minutes. And these cables were laying around, so there's no tension in the cables. So if that thing would have got past that lip, which it could easily, it would fall 18 feet. So these guys that are running the thing are like three blind mice. They don't know what they're doing. They can't see what's going on. They can't hear what's going on. They don't know what's going on. It's sad, pathetic design. I mean, they knew it was this bad. And there's some other things wrong with the design, but this is one of the worst features. So let's suppose we drop the cylinder, and it hits the bottom concrete. It'll hit at about 23 miles an hour. This is the kind of problem that you give freshmen to do in the physics class. So yeah, cylinder drops, has a mass M, goes 23 feet. It goes 18 feet, we're hitting 23 miles an hour. When it hits, you can calculate the energy of the bang there. It's equivalent to 2 large sticks of dynamite or 2 megajoules. Now you can be sure that that's going to wreck hell with the surrounding structure there. And remember, those canisters are real close to each other. You could easily get a problem where the intervening space gets messed up and it causes the canisters, the ventilation system to fail. If that ventilation system fails, there's nothing to keep this thing from overheating. So if it overheats, you basically get into the zirconium problem that we talked about earlier. And if there's any water around, the thing is going to explode. In addition to this 2 sticks of dynamite here. So that's a very dangerous thing that they didn't even choose to report to the public. It's also equivalent, if you take like an 18-wheeler truck, fully loaded, it's equivalent to that truck smashing into concrete at 23 miles an hour. Crash, you can see this is a model of what it would look like. Crash is bad for the concrete, wrecks the concrete, bad for the truck, and bad for the contents. So basically, the Nuclear Regulatory Commission did a study many years earlier of what would happen to a spent fuel canister that was under these kind of conditions. And they basically concluded that it would split open. So if you have a split open canister, the thing's heating up and water, you're going to have an awful situation. Also, there's a specification that they have, which is kind of an interesting thing. It's called a tornado generated missile. Just picture like, what shall we say? What experience would you have with tornado generated missiles? Let's go to the Wizard of Oz. This is Dorothy's house. This is the tornado. This is the Wicked Witch flying around there, and this is the Auntie Anne. So it's like a big telephone pole flying around there with that house and hitting the thing. So basically, this falling canister would exceed the specification for this tornado-generated missile by a factor of 4. And we showed this to the NRC and talked to them about it many times, and they basically just weren't interested. They were not interested in the fact that this basically exceeded their specifications. So that's a shocking kind of organization to work with, because you think they're on the side of trying to keep people safe, and on these issues they don't appear to be on that side. This is what the thing would look like. The ISFC would look like if you made a cross section of it. You basically have, this is the ocean out here, and the tides go up and down. This is the mean high tide here, meaning sometimes the high tide is higher, sometimes it's lower, but that's the mean there. And so the mean high tide would come over here along this line here, about 18 inches below the bottom of the canister today. Now, there could be some groundwater from the hills and whatever, but let's just assume there's none here. So today, let's say there's an 18-inch gap there before the water would get to the bottom of the cylinders. Now, Jim Hansen, that we talked about earlier, made a prediction that sea level rise is going to rise about 10 feet by 2065. That's fairly soon. So if the sea level goes up 10 feet from this current situation, what we see is the canisters would routinely be in salt water. They would be, a couple feet in salt water routinely. And these things aren't designed for that. And so what happens is you're going to have a corroded, and the thing is already scratched, so the scratches are going to grow a set of cylinders there. It's a very, very bad location. I'd like to introduce you to a few of the people that worked with me on this. We formed a little team of people to do the nuclear waste analysis. The idea was you don't want to get stuck alone on this sort of thing, because it's good to have others to talk to so you can make sure that what you're doing is right. This guy is called Subrata Chakraborty. He is a guy who normally spends his time looking at samples that came from a spacecraft that were launched to essentially capture particles that are floating around from the sun. And so he had all this fancy equipment in the back there. It allows him to basically see what is in the solar wind. So Subrata, this is a picture from one of the videos that we were involved in. This is another guy who was involved with our team here. He and I were doing a duet at KPBS. This is Greg Yasko. He's the former chair of the Nuclear Regulatory Commission, and there's me. We put a report together, me, Subrata, and the guy you'll meet in a minute here, Rear Admiral Len Herring, basically on what the main issues of nuclear waste are. In the report, we said there's a very bad location. The equipment and processes used to move the nuclear waste are poor, and the management is really defective management of this facility. So you got three major things wrong with the facility. It led to the Nuclear Regulatory Commission shutting them down for a year, and they then let them get back working again without really fixing the problems. This sponsored Congressman Mike Levin to form a nuclear waste task force. And here's Greg Yasko. He's on the task force. He's the co-chair. And there's Rear Admiral Len Herring. He's the co-chair of the task force. I was on the task force also, and so was Dave. So there we go. More questions.
We have several. Charles Langley is asking if you could talk more about fusion. Does fusion have spent fuel risks?
Let's see, fusion. Well, we can talk a little bit about it. Basically, it's how the sun works. There's this fusion reactor, whatever it is, 86 million miles away. Works fine out there, day and night. The problem with fusion is one of the problems is the problem of schedule. I first got involved in fusion at Project Matterhorn, which was at Princeton, back in the, this is the, around 65 or so, something like that. The basic concept was they were going to basically contain this plasma and have these reactions, these fusion reactions, where you basically take various things like deuterium and tritium and smash them together, and they fuse together to form helium, and it gives off tons of energy. So anyway, the schedule was they're going to be doing it in a serious way in 20 years. So that would have been, let's say, 85. And in 85, the schedule became 2005. And today, this is around 20, so the schedule would be about 2040. The schedule keeps slipping. They are making progress in terms of the ability to contain the reaction. They contain it longer and longer. Still not very long, but longer than it used to be. The problem is with it, I think the major problem is that the design of the facility requires an awful lot of high energy neutrons floating around. And those neutrons will interact with the surrounding facility. And when the neutron bumps into a piece of metal or something, it can essentially wreck the piece of metal after a while. So the idea is you're basically converting the structure surrounding this fusion reactor into dust. And let's hope they can figure out a way to do that. But until they seriously work on the idea of what's the structure going to be like, they're not going to make any real progress on fusion. So I wouldn't, in terms of any issues that are facing us today, like say climate change or whatever, I wouldn't put any money into fusion because it's not going to be available on a time schedule that's of any interest.
Russell asks, could dry waste be dumped into the sun? Is our space technology up to that?
One of the things that I was involved with at my job at JPL when we had this nuclear waste team together from the Jet Propulsion Laboratory, from Caltech, and from Scripps Institution of Oceanography, is we looked at the options of space. It turns out you could dump the waste into the sun, but if you did that, it would take twice as much energy as it would take just to get it totally out of the solar system. So, you know, that was an option that if you took it, would be dumb in terms of energy. There are some other options that we looked at in space. We looked at putting it in a parking orbit between the Earth and Venus, or putting it in a parking orbit between the Earth and Mars, putting it on the moon. This was during the Carter administration. And so we had the effrontery to pick a crater on the moon that was named Billy, you know, the crater Billy. So that it'd be like Billy, Jimmy Carter's brother. So anyway, we looked at all those, and the basic thing was killed by one of the budget examiners who basically asked, oh no, an NRC commissioner who asked me the question of, well, suppose this thing blows up on launch in Florida for just one of the launches, one of the many launches. What damage would that do? And the answer is you would have to abandon roughly a third of Florida. So his question was, why are you bringing us this 100,000-year problem all in one afternoon? So I don't see any hope for space at all.
Okay, and then Sarah asks a question that I know is also on the minds of many involved in this issue, and that has to do with the canisters. Will you be addressing the issue of the thin-walled 5/8 inch thick canisters versus the thick-walled ones, casks that are 10 to 19 inches?
I'm not really going to get into the details of design. We can talk a little bit, during the free-for-all Q&A session, but basically, I'm not going to be pushing, oh, you have to go with the German design, or you go with a Swiss design, or whatever. That's a detail. I'm just trying to get you the big picture as opposed to the detailed answers. But I think you can design the canister that will work, and I think that you have to then put it somewhere where that canister will be safe enough. I think those are doable things. And I think we should get on with doing that, but we haven't done it yet.
Right. Okay, and then Mark is asking about the dry storage. So how does the dry storage example you showed work? Yucca Valley is a dry storage method facility. What are the specific problems with storing the waste near the ocean? And then what's the challenge tied onto that? What's the challenge with sea level rise here? How many years until the San Onofre spent fuel containers go into water?
Well, let's do the last question first. I think the number that we had there was in 2065, which is not too far in the future. The canisters will be several feet underwater. I mean, the bottom of them will be several foot in the salt water, which is completely unacceptable. Because why don't you just go and throw the darn thing in the ocean to start with? You'd say that's ridiculous. Well, it's just as ridiculous to have the container where it is. So that was the last part of the question. What was the first part?
It had to do with just explaining the dry storage example that you showed. What are the specific problems
the idea of
storing into the ocean?
Yeah, the idea of dry storage it could be a good idea if it's designed properly. Because what you want to do is store the thing somehow so that it's not going to heat up. So you have a thermal problem there, and you can design the thermal problem so it'll work. You want to also make sure that that the thing's not going to corrode. I believe you can do that fairly sensibly. And you can also find a geological system for it that'll be good for the geologist. Will guarantee it for that 10,000 years. And they don't want to go for 100,000 years because they just don't know how to do the geology on that time scale. The science isn't there yet. So I would say go for it. Let's look at some economics here. This is a different viewpoint. This is a report put together by Richard McCann and Elizabeth Styreski. They live up in Davis, California. And what they did is they basically says, if you have an event like the one that almost happened, where the canister dropped 18 feet, what would be the economic consequences of it? So basically, they examined the impact of that kind of event over a distance of 50 miles. So we're talking about affecting things from Torrance, Long Beach, Ontario, Hemet, San Diego, Alpine, it's just on the edge, Julian's just on the edge. So this is a big slice of real estate. And so what is the economic impact of essentially something going bang in that area and causing us to abandon the area, just like the Russians did in that example I gave you earlier? Their bottom line is that the cost over roughly a 50-year period would be about $13.4 trillion. That is a lot of money. And that's the kind of money that could wreck, Southern California, could wreck the economy of California, might even put a serious dent in the world economy. So it's big bucks, and it's something that you should avoid. This is a guy who looks into some of these issues. He's really good at doing the economics. He's also good at doing the science. His name is Amory Lovins. I've known him since, my early days at JPL. I met him, he's a visiting kind of consultant, I'd call him. He's worked for kings, queens, prime ministers, whatever, all over the world, presidents, very famous guy. He's the first one to basically show that the US could save an awful lot of money by adopting better energy strategies. Anyway, I met Amory at JPL. I was in a bad mood one day, and this guy was coming to give a talk, and so I'm there, and I'm looking kind of glum. And he said, "What's wrong?" I said, "I'm just feeling glum." So he comes up to me and gives me a back rub. So I thought that was a pretty good introduction to the guy, a back rub. And I've been following his activities ever since. He's done an analysis here that says, does nuclear power slow or speed climate change? And I thought I'd share this with you because it's kind of an interesting analysis. What he concludes is that most nuclear power plants, most meaning about 3/4 of the US nuclear power plants, cost more to run than they earn. So they're losing money every day. It's like a charitable organization that we taxpayers happen to be paying for. He also says that if we take like one of the best nuclear reactors, not the ones that are real dogs, but one of the best ones, it costs so much to get energy out of that, a certain amount. And we could buy the same amount of energy by buying efficiency improvements. You could save $20 to $30 per megawatt hour. This is an enormous savings. So his conclusions are that building new reactors or operating the most existing ones makes the climate change worse compared with spending the same money on more climate effective ways to deliver the same energy. So if you can go out and buy say a wind farm that will give you energy for so much expense for a kilowatt hour, then if that expense is a half or 3 or 4 times less than the cost of keeping a nuclear reactor just running, not even building the reactor, but just running it, then you're foolish. You should basically shut that puppy down and basically shift to something that gives you the same energy and that's much cheaper. So that's basically his thrust. This is Dr. Jim Hansen. I mentioned him several times because he's one of my big heroes. He's been testifying on climate before the Senate more than anybody else on the planet, essentially. And what he says is that nuclear power is the only viable path forward on climate change. So he says you absolutely need nuclear power in order to solve your climate change problem. So here we have 2 guys that are both superheroes of mine in complete contradiction with one another. So it's a classical problem that you see in science. the science is like public arm wrestling. What you do is you basically fight in the court of public opinion. And basically, after a while, if your argument is weaker, you have less and less followers. And pretty soon, you're not the winner in the scientific community. So this is a perfect example of that. And I'll give you an example here. The LA Department of Power and Water has bought a system. It's a solar system that has battery storage. They're paying 3 cents per kilowatt hour. It's cheaper than electricity from natural gas, which of course is much, much cheaper than from nuclear. And it supplies 6 to 7% of the needs for LA. And it's good for 4 hours each night. So that's the kind of competition the nuclear guys have, and they can't beat that competition. This is a analysis here done by a group called the Energy Information Administration, part of the US government. And what they tend in the past to be very pro-nuclear. So this is some projections. Here we are now, say 2020, and they're projecting what things are going to be like in the future to the right of this curve here. And what you see in the curve here is you see a lot of yellow for solar, some green for wind. They have some oil and natural gas in there. You notice nuclear is only below the line. Below the line means plants being retired. So basically they're projecting out to about 2050 with no new nuclear power plants in the US. So I think this kind of graph here is very significant in the fight between Hansen and Avery Lovins. This basically says that the bankers and people like that are really on the side of Amory, and that Jim had better just stick to his climate change work as opposed to getting involved in power plants. It just says there aren't going to be any new nukes, period. Bill Gates, though, gets involved in this, and this is interesting. He's come out with a book, How to Avoid a Climate Disaster. I've bought the book. I've probably read maybe 50 pages of it. It reads really well, and his stuff is, I like it. He basically says the current nuclear power plants are not good. The waste problem appears to be intractable. And what he wants to do is to build a new kind of nuclear power plant called a traveling wave reactor to basically help out with this. So I'm trying to understand his traveling wave reactor. I'm a little bit of a skeptic, but I'm going to give him the break and see what happens. So here we go. Okay, now we're open to the free-for-all question period. So, okay, Dave, you got it.
Rob asks, can the rods be recycled into fuel at all?
Yes, they can. In fact, there were 2 different views of that. One was the view of General Electric. The other view was Westinghouse. When Westinghouse made these assemblies, what it did is it basically sold you the assembly and the uranium, and it's yours, forever. Don't come back to us with it. GE says, we refuse to sell it to you. What we want to do is we will lease it to you because we want you to return it to us because we're going to reprocess that spent fuel and make a lot of money reprocessing it. Now, got the idea so far. So it's make money if you're a GE with the fuel. So I was working for GE and got to spend a little bit over a month or so at their attempted reprocessing plant at Morris, Illinois. What they did is they built this plant on about 400 acres. It's near some water, and the buildings some of them are maybe 8 stories high, so it's a fairly extensive installation. The floors where they're actually trying to reprocess the material were about 4 feet of concrete thick. In order to see stuff that was going on in the area where they were reprocessing, what they did is they bought telescopes from nuclear submarines. And so you would basically look down the periscope, and I've done that to see what was going on. The idea was you basically take these fuel assemblies, chop them up into little pieces, perform some chemistry on them, get rid of the metals, And then you basically have the plutonium going one direction, the americium-241 going another direction, and then you collect the plutonium, you collect the americium-241, et cetera, and you basically take that stuff and you make new fuel rods out of it. So you make yourself a fortune. So that's the idea. So what happened is they built this big thing, they turned it on, and it actually worked for about a half an hour. And then the pipes got all clogged up because these are very high temperature materials. And these materials tend to be, they call them refractory. And they just basically clogged the pipes. So what they had to do is shut it down after half an hour and clean things up before they did it again. Well, I think it took them a year or so to clean things up. And because it's intensely radioactive inside these canyons where they're working, and they're very dangerous work. And so they got it cleaned up again, and they were going to try again. So they tried a second time. This time they had a vice president there of GE. And this time it worked much better. It worked for an hour as opposed to a half an hour. So what happened is it clogged itself up after an hour of working. And the vice president of GE basically had the people taken out of the facility. And he basically walked up to the fence. There it had a chain on the fence. He had a padlock. He padlocked the thing closed. So that was the end of General Electric's effort at reprocessing. And no one in the US has tried it since. So it appears that it's a very, very difficult thing to do. The French were successfully reprocessing, but what happened is their system was different. They basically didn't have a commercial and a military side. They were glommed together. So you can never tell where the expenses went. Was it to the military or to the commercial side? So the way the bookkeeping worked out is the commercial side looked pretty good, but then they separated the two. And when they did that, they began saying that they weren't making any money on the commercial side. So they're trying to get out of nuclear as fast as they can. So I think that gives you some idea that there's not going to be any money made any time in our lifetimes, okay, out of this reprocessing stuff.
I actually just wanted to make a comment, Tom and Dave. I just happened to notice in the paper today that Southern California Edison just put out a 3-volume report on relocating the spent fuel from San Onofre. And there's an article about it in the San Diego newspaper, Union Tribune, I think 2 days ago. I think they're on your side. They want to get the stuff out of there.
Oh yeah, they this has got to be a real pain for the utility. I mean,
Yeah.
Why they hate this stuff. So yeah, they want to get rid of it. But basically, what I read is they want to move this to somewhere whenever the opportunity occurs. And there was no specificity of it. So I think they need to do better than that. I think they need to, actually get something seriously going. Like one thing would be you could take a piece of wood and carve the name interim storage system on it and stick it up at Yucca Mountain. But they would probably, when they did that, they would find out that they had problems moving those canisters that they now have, on existing rail platforms. So it needs to be done, but I hope to see more than just PR out of them. I hope they actually do something that's useful.
I grew up around the Hanford Atomic Place back in the 40s and 50s. So I kind of grew up with atomic energy, I guess, and nuclear problems and so on. As far as I know, there have been a lot of long-range studies of effects of radiation around the Hanford area. None too awfully serious from what I've heard about that. Other places, Rocky Flats or whatever it is in Colorado, I guess they had some serious problems around there, and various other places, but no long-range effects. Then I did have a question. I don't know if you talked about tsunami dangers around San Onofre. They seem kind of minimal. If it was Crescent City, I'd be a lot more worried.
Well, my friend Subhatra did an analysis of tsunamis in the San Onofre area. And he was concerned enough, given the current design, that should be something they should look into more seriously.
But there haven't been that many serious tsunamis around the San Onofre area over the years. I don't know, geologically speaking, or.
Yeah, he referred to one back in the, I think it was 1880 or something like that, that wasn't included in the analysis of SCE. And his conclusions were that that should have been included before they put that thing at the location that it's in now. He concluded that the location was unsuitable based on that alone.
Yeah, okay.
And I might add, I know that one thing that could really trigger tsunamis is an earthquake, and we are overdue apparently, according to most of the geologists, for an earthquake. So I think that might be one of the factors, right?
Sure.
Yep.
Yeah, that's how many big tsunamis get started. There's an earthquake, and part of the earth slips down, and the wave goes down, and off comes the tsunami.
And my daughter lives in San Clemente. They still have the tsunami air raid sirens installed there. It only takes one tsunami to bury San Onofre in water. So.
Yep, that's right. Could you discuss the pit corrosion potentials from the carbon steel particles that were embedded into the stainless steel when the canisters are gouged against the carbon steel guide ring?
A little bit, yeah. Basically, what we did is we invented a new technique for predicting how big the gouges would be in the canisters, and basically just using basic physics. You can, there's information that's available. You take a hard ball of material and you put a pressure on it. That'll make an indentation in so big, and then if you drag it across that slowly, that indentation will become like a large gouge. And so in the report that we put together, it has the details of how wide the cracks should be and how long they should be. And the limited amount of data that we had in terms of actually being able to check it out indicated that our numbers were pretty good. So we basically were worried in terms of the crack propagation. You basically take a crack and you stick it into salt water, which Subhadra did in his lab, and he found out that the cracks grew at a significant rate. So they basically didn't, their argument is that these cracks aren't significant and therefore don't have to worry about them. Yeah, but we concluded they were significant. So, it gets into a kind of an arm wrestling contest among the professionals. I would bet on them being significant. We gave testimony and we wrote reports and we argued with the people.
Have you looked at the repair technology that Edison presented as a remedy for this?
This was some stuff that came out of EPRI, okay?
Right, but Edison.
I'm sorry. Edison got its stuff from EPRI, okay?
Right.
Electrical Power Research Institute. And basically it was like they have a little robot moving around doing some stuff. It was mostly for taking pictures. It really wasn't for repairing.
Well, they presented to fulfill their permit requirement with the Coastal Commission. They had to show that the canisters are transportable. So they presented a nickel spray coating that they intend to put over these gouges. And so I'm wondering what your information is on whether or not, I mean, my research says it's absolutely ineffective. It has not been approved or even analyzed by the NRC, yet they let that be a viable pathway forward for Edison's decommissioning permit to happen. So that nickel spray, cold spray repair technology is a big sham as far as I'm concerned. You might want to look into that. Well,
it's, I honestly haven't been doing nuclear for about maybe a year and a half or something like that. But yeah, it sounds to me like you're asking for a sensible thing. That is, they say we have this wonderful technique that will solve the problem. And it would be nice to then have people discuss the technique, have some demonstrations that show how it actually works. And you're basically saying you're skeptical that the thing works at all. And I think that's a sensible position until someone proves it works.
It's certainly never been used on a nuclear pressure vessel with a half-inch or whatever, inch and a half space that they have to work within. But anyway, thanks so much for your presentation.
Rob has his hand up. Rob, go ahead.
Hi, Rob.
Hi. Yeah. Oh, this was great. This is like super scary, So I take it that these fuel rods, they're always decaying, but, the way things are managed, they don't get too hot. So if they're dry, right, and you don't get the production of the hydrogen, but you do have to like circulate air through these cans to kind of keep the temperature down. How do you keep them cool?
What they do is they basically, on the inside of the can, they have some helium. And the helium the hot helium goes to the top, the cold helium goes to the bottom, and it basically acts like a convection loop. So that's how they take the heat out, essentially. Then it goes into the walls of the canister.
Like a pipe, like in a computer, like a heat pipe.
Exactly, just like, or like the old-fashioned stoves they used to have on furnaces, where they would put pipes in the furnace to actually get the fireplace to give off heat. But anyway, that's their design, and there's some questions about, does the thing leak, and what does it leak? And basically, I've never seen a good, thorough analysis of the whole system, because I was one of the ones asking the questions about the leaks. And their answer was basically, you don't even need the helium in there. If it leaked, it would still work. So the answer that they had is that if anything happens, it still works great. Now, I don't believe that. So
Believe that. So in theory, it's a self-sealed system that just kind of radiates the heat.
yeah, that's the basic idea. And if what happens in the countries where they have basically thick walls, it makes the heating problem a lot easier to solve.
So if we're dubious about being able to recycle this stuff, and even saying that if you could recycle, you're still stuck with a problem. If you moved away from power generation or for the public, could you just be left with a niche market where you had submarines and naval vessels using nuclear in the future, and the rest of it just going away?
Well, if you look at, say, reprocessing again, suppose you say, I don't care whether I'm making any money or losing money, I'm going to do it anyway, okay? Then basically you would be taking out stuff like plutonium. Now just think of using plutonium as an item of commerce in your economy, okay? And how soon that those items of commerce are going to leak into the hands of people that want to make things go bang in the night. Not a good idea. We have a tough enough time keeping track of the uranium and plutonium inventories now, but if you make it into an item of commerce, it's going to be far worse. So it's just not a good idea. It's like, okay, you made a mistake. You've got this technology that doesn't work quite right. Don't make your hole digger and digger.
Yeah, okay. And Dr. Hansen's book, Storms of My Grandchildren.
Great book.
Yeah. So I think he said, I'm not a nuclear expert, he said, but I think he said the new generation of breeder reactors or whatever were like 99% efficient, as opposed to like 1% efficiency from the other generation. But then you raise the issue of basically plutonium getting out and the security issues. You want to comment on the trust factor and all that, 99 versus 1, that's kind of interesting.
Well, do you remember when nuclear first came out? I remember I went through the shipping port reactor before it was opened. And it's kind of interesting to see the beautiful stainless steel plumbing in there. But the basic idea was this energy is going to be too cheap to meter, okay? We got this wonderful machine here. It's going to be too cheap to meter. That's how good it is. So it's nice if you're inventing something because you can make the numbers whatever you want them to be. So I just don't
You don't-
trust the numbers.
Okay. Okay.
Okay, so Sarah has a good question that on another kind of related issue, which is can the existing canisters at San Onofre be safely transported if a storage site, interim or permanent, ever becomes a reality? Some have argued they are not safe for transport. What's your take on that?
Well, my question is really not the question of safety, but it's the question of would the Department of Energy accept the darn things? Because they have some sort of criteria before they're going to let those canisters get aboard a little train and take them somewhere in the country. So I think that's the issue, and I think that they don't know how safe those things are. I mean, right now we have this thing. Remember when we had the bolts rattling around in the bottom of the canisters? And what was the answer? Well, we're just we'll get to that later when we get some spare time. You know, now, I don't think you'd want to have a canister romping around the country with bolts rattling around in it, because these trains bounce around or whatever. And I doubt that there's any specs or any tests done for bolts that are rattling around inside that kind of canister. So it's like there's just a whole host of things that are ordinary, I would call them childlike questions that they refuse to even look at.
And that's what makes you scratch your head on this whole issue, really, is the NRC's kind of role and take on this whole thing. You just can't quite figure it out. But Nina's got a good question here, sort of related. Were the utility companies a part of the nuclear warhead reduction negotiations? Are we stuck with utilities' commitment to supply exit strategy for warheads via nuclear waste?
The little bit that I read indicates that this is a government kind of thing, and they basically get contracts with companies to take the MOX and essentially make pellets out of it. So the utilities wouldn't be involved at that level. They basically would like San Onofre, they've burned up a considerable amount of MOX at San Onofre. And so they just say, well, to them, it's just another fuel. You have to put them in slightly different parts of the reactor so it doesn't get too hot. To them, it's just basically another fuel source. I don't know if that answers your question, but I think that the DOE is the place that would have the major management responsibility of what to do with that stuff.
Any other questions that anybody has right now? Were you going to have a discussion about the grid system?
Well, the basic the grid analysis was twofold. First, it was looking at the Texas grid and basically seeing how the wind systems on the grid interact with the photovoltaic systems on the grid, and how you can do things that basically load level. Like the issue is, how do you get the thing to work at night? When the photovoltaics isn't doing anything. So that was one issue. The other issue is, how do you then take a grid that has whatever demand curves it has and start to put all these newfangled technologies, these renewables on there? How does that affect the old fossil fuel stuff? And how do you keep making money? And how do you keep operating the grid so that you don't have too steep a ramp where you're changing from the lower values needed of energy to the higher values of energy? So anyway, those are the two pieces. The second piece is called, they look at the shape of the curve that's the demand curve, essentially. It looks like a duck to them. So the question is, how do you make a duck fly? So that was the essence of the talk, the second part of the talk.
Okay, and Rob, you've got your hand up.
Kind of a science fiction question. So I guess, like they say in Star Trek, we violated the prime directive. If the prime directive is don't take toxic things from the core of the earth and bring them into the biosphere. So is it possible to dig down deep enough into the earth where you have these invaginations of the mantle taking place, and it's radioactive down there. And you could take all this shit we don't know what to do with, plastic and this, and just kind of put it in there and have it reconstitute back into the core. Can you imagine, or would that just make more series of problems?
Basically, one of my friends looked into that. His name was Sir Edward Bullard. And what he basically, the thought was you would drill some holes next to a so-called subduction zone, okay?
Yeah.
The subduction zone is basically part of the system that's going down, okay?
Right.
But basically, you put this stuff in the subduction zone and it goes down. He pointed out that these subduction zones are not well behaved. And some of them have little eddies that come off, and the eddies go up. You may be just putting this thing down there temporarily and then causing it to come on in the form of a volcano. No,
Okay.
it's worse than your science fiction idea, because what you're saying is you go down the earth and you dig things out and you bring it to the surface. What we did is we basically took stuff that was fairly innocuous and by very clever techniques made it into something extremely dangerous, namely plutonium. The plutonium did not exist on the earth before that. And so all of a sudden we now have a lot of plutonium. So it's like we weren't very smart.
So it's not a natural element.
No, but because the half-life is about 24,000 years. So, if you have something hanging around for a million years or so, there's none left.
Nina's back, and she has another question here.
I was just wondering if the utility companies were a part of those nuclear weapon reduction negotiations, Tom, and if so, are we kind of locked into using up the nuclear warheads to extend the life of the nuclear industry? I mean, is there some kind of connection at the hip there? And then my other question was related to the chart from the MP study that, the 50 mile radius. And, since it can't be contained, isn't that really something that could migrate to other parts of the country and the world just with the wind?
Well, the 50 miles comes from the limit on the NRC model that they use. Their meteorological model goes out 50 miles. So we wanted to use their model. So we said, okay, 50 miles. I mean, sure, the things spread out further than that, but it's just, we didn't have a modeling vehicle to use.
Yeah. I think there was somebody who did some kind of a modeling. And Charles, I don't know if it was the gentleman up in Napa or who was it that had a migration map that was done. But at any rate, Tom, I'd love to hear your answer about, the nuclear warhead negotiations and whether or not we this is a recycle type of thing that the utility industry is committed to until those are drawn down.
Well, let me give you a feeling for the warheads. Back in the old days, before the nuclear freeze was effective, we had, let's say, 100,000 warheads, okay? And we're now down to the scale of, let's say, about 5,000. So 95% of the problem in terms of the warheads is already been taken care of, and that's already in the in the pipeline. It's been in the pipeline for years. So I doubt that there's that 5% left is not going to be enough for the utilities to bet on at all.
I see. I just never knew of that connection before your presentation today, so I really found that very, very interesting.
Well, thank you very much. Yeah, it's the connection between the military and the military issues and the civilian issues has always been at the heart of the nuclear issue.
I knew that. I just didn't realize that it was part of those negotiations. And that was very, I found that very interesting.
Well, what happened is, neither side trusted the other side. And so basically you can promise any reduction you want to, but you're not going to believe it unless there's some sort of mechanism in the treaty that basically guarantees that you give up your fissile material. So you have to basically take the uranium and plutonium in the warheads and do something with it that makes it unusable for warheads. So that's
Really
what they
appreciate your presentation today, Tom. Thank you.
Well, thanks, then.
Okay, well, again, thanks everybody for attending today, for your time and your great questions and interaction. And we look forward to seeing you again next week. So have a great day.
Bye-bye. Bye.
Ta-ta.
Bye-bye, everybody.